Here are the notes for section 17.3, the electric field. Again, we're going to draw an analogy from gravity. Now in gravity, we say that F equals ma, force equals mass times acceleration. In particular, in Earth's gravitational field, we say that F equals m times g, so we have a specific value for acceleration, g, and we can rearrange that to define acceleration as force divided by mass, or acceleration of gravity equals the weight of an object divided by its mass. And this is a measure of the Earth's gravitational field strength. It tells us the magnitude of acceleration acting on a piece of mass is the force due to gravity divided by its own mass. All of us on the surface of the Earth are under the influence of 9.8 meters per second squared. Our mass is insignificant compared to the Earth, so we all feel the same acceleration. Now, we're going to use the same idea for the electric field, but instead of dividing by mass, we're dividing by charge. And the quantity that we develop is E, and this is called the electric field. And just like G gives us a sense of how strong the gravitational field of our planet is, E gives us an idea of the strength of a charged object, a large charged object. And I like to think of these large charged objects almost like planets. And then we bring a small positive test charge near this large, almost planetary charge, and we see what happens. The electric field, this is the electric field at the location of Q naught, produced by the charge big Q. Again, that's our planetary charge, and not the electric field produced by the test charge. You wouldn't think about the gravitational field produced by you, right? You're thinking about the gravitational field produced by the Earth. And the same thing here. We're thinking about the gravitational field, the electric field produced by this large charged object. But in order to measure it, we need to have a small charged object. The electric field is a vector pointing away from positive charges and pointing toward negative charges. Now, this is a little bit different than gravity. With gravity, it always works in one direction. Gravity is always attractive. But electric forces can be attractive or repulsive. So some of the consequences of that are not what we would expect because we are used to a gravitational force that is always attractive. There's a formula for calculating electric field strength. The formula for calculating electric field strength, and this is due to a point charge. Or planetary, think of it as kind of a planetary model. It's equal to K, that's this value we used in Coulomb's law, times Q, where Q is the planetary charge that we're measuring, divided by R squared, where R is a distance. Let's take a look at an example. A test charge of 3 microcoulombs is at point P, where the E, the electric field, is directed to the right with a magnitude of 4 times 10 to the 6th newtons per coulomb. If the test charge is replaced with a charge of negative 3 microcoulombs, the electric field at P, what happens? Okay, so let's suppose for a moment that we've got this charged object, this 3 microcoulombs, okay? And the electric field is to the right. So we said that the electric field points away from positive charges, which means it's going away in all directions, and we'll talk more about that later. But we must be on the right side of the object if the electric field is going to the right, and we've got point P. The idea here is that the electric field due to this object, due to the 3 microcoulombs, does not change due to the test charge. So the electric field due to this object remains the same. Just like the gravitational field due to the Earth doesn't change when you put a different object near the Earth. So I could clarify this just a little bit. The electric field at P due to the positive 3 microcoulombs remains the same. Let's look at example 2. A free electron and a free proton are placed in an identical electric field. Which of the following statements are true? A, each particle is acted upon by the same electric force and has the same acceleration. Now, they would experience the same force, but because they have different masses, they will not experience the same acceleration. B, the electric force on the proton is greater in magnitude than the force on the electron, but in opposite directions. The opposite directions part is correct, but the magnitudes, again, are going to be the same. The electric force on the proton is equal in magnitude to the force on the electron, but in opposite directions. Yes, this is true. The magnitude of the electron, the magnitude of the acceleration of the electron is greater than that of the proton. This is also true. Both particles have the same acceleration. No. The particles have different masses and therefore will experience different accelerations. Let's take a moment to talk about electric field lines. We're going to use electric field lines to model the electric field created by a charged particle. Here are the 5 rules we need to follow when we draw electric field lines. They begin on positive charges and end on negative charges. They are normal to the surface of objects. Remember that this word normal means perpendicular. The number of lines per unit area is proportional to the magnitude of the charge. It gives us an idea of field strength. We cannot cross the lines, and the electric field itself is tangent to electric field lines. This is important to know when the lines are curved. So let's draw some electric field lines if the charges are equal and opposite. So we already said that the electric field lines go out of the positive and into the negative. Oops, I can do a little better here. Is it sufficient just to draw one field line? The answer is no. Your field lines should demonstrate the shape of the electric field. Again, I'm trying to follow some rules here. I'm showing that the field is normal at the surface. And it's also important to recognize that when we have 2 charges like this, that the field will bend. And this looks a lot like what you would get if you worked with magnets. So all of those field lines are curved. All of them go out of the positive and into the negative. And if I count the field lines around each object, 1, 2, 3, 4, 5, 6, 7, and there's 7 around the other object as well, that indicates that the charges are equal in strength. What about if the charges are equal and have the same sign? I'm going to actually redraw this down here where I have a little bit more space. I've got 2 charges that are negative, which means the field lines will be going into I draw my arrows, they're going to go in. Again, whenever I have 2 charges interacting, all of these field lines must be slightly curved. Oops. I've got 6 here. I need one more. Oops, I really move this guy just a little bit. Let me get rid of him. Okay. All of the field lines are curved because the two charges interacting with each other warp or bend each other's field. Now let's talk about what's happening in the center here. Right at this point in the center, there is no field. Why? Well, if I put a charge right at that center point, and it doesn't matter if it's positive or negative, but just for the sake of my example, let's say I put a negative charge right in the center, what's going to happen? It's going to be attracted to the right, it's going to be attracted to the left. And what's going to happen is these two forces are going to cancel. So that effectively, exactly in the center, right in the center here, the fields do cancel because the forces on a charge cancel. So there is no field right between these two charges. And my field lines show that. My field lines show no field right in that center. What if the charges are not equal? In this case, I have opposite charges. I would want to demonstrate that with my number of field lines. So I'm going to start out by drawing field lines that look like my first picture. Again, all those field lines are curved, except for the one in the middle. The one in the middle, right down the center, looks like that, but the rest of them are warped. And it says the positive charge is twice in magnitude, which means the positive charge must have twice as many field lines. So because I have 1, 2, 3, 4, 5, 6 here and 1, 2, 3 here, that indicates that the positive charge has twice as much charge as the negative charge. I want to take a moment now to talk about